Okay, so now for some more actual calculation of probabilities using our Venn diagrams and union and intersection notation. Okay, so we're going to use an example from another video, this one here, where we have a situation with 150 students who are studying biology, chemistry, or both, or neither. Okay, and we've already put them into this Venn diagram. Okay, we've already calculated how many study both. So our question is here, well, we've seen before that A or B in some situations can be found by just adding the probability of A and B. Okay, but an important note for that is that only works when the two events are mutually exclusive. And that means they can't happen at the same time. Now, in this example here, we clearly can have both things happening at the same time. Okay, so how do we calculate the probability of B union C, i.e. B or C or both? Well, one might think, well, do we still just add them? 85 plus 64? Well, we get 149 out of 150, and that's clearly not right, because we have 17 students that study neither subject. So what has gone wrong here? Well, we counted B, that was our 85, and then we counted C, that was our 64, but you can see just from the shading here that I've shaded in the intersection twice. Okay, I've counted those 16 people that study both subjects twice. Okay, so what I can simply do to adjust for that is to subtract one of those 16s, to subtract the probability of the intersection after adding, to avoid counting it twice. Okay, and what I would find is 133 out of 150, which would fit very well with our 17 students that study neither subject. Okay, you could say that this is the probability of a student studying at least one of biology or chemistry. Okay, biology, chemistry, or both. Okay, and it needs that special adjustment, subtracting one of the intersections because, well, to avoid counting it twice. Okay, so can we sum that up in a nice formula though? Well, it should be easy enough. So probability of A union B is equal to, well, add them up as we usually would, but subtract one intersection. Now, you might think, well, how do we know when to use which formula? When do we just add them? When do we subtract this intersection? Well, the good news is that this formula actually works all the time, because when two events are mutually exclusive, then the intersection does just equal 0. Okay, so it really doesn't matter if you use the full formula, because all you'll be doing at the end is subtracting 0, and obviously that doesn't do anything. Okay, so this formula always works. Okay, unlike the formula above, that only works for mutually exclusive events. Okay. Finally, we have conditional probability. Now, a little bit more complicated concept here. What if we are asked a question like this? Given that we choose a chemistry student, what is the probability that they also do biology? Okay, so given that is the very important part of this sentence, as you'll come to learn. Okay, it gives us some very important information, okay, and means that we are essentially not even considering all 150 students anymore. Okay, so you might think that this probability could be 85 out of 150, okay, because that's the number of biology students, okay, but that just completely ignores the first part of this statement. Okay, that would just be the probability of biology. You might think 16 out of 150, because that's the number of students that do chemistry and biology. But that would be the probability of the intersection, and that again ignores the first part of that statement. So how do we take this into account? Given that we choose a chemistry student, what does that tell us to do? Well, it basically tells us to discount any student that does not study chemistry, okay, and just focus in on these 64 chemistry students. Okay, so we are no longer out of 150, we are going to be looking at a probability out of 64. Okay, and which students do we want? Well, we don't want all 85 biology students. Now we are looking at picking just one of these 16 students, okay, because those are the ones that also study chemistry. Okay, so we end up with 16 out of 64, which would simplify to 1/4. Okay, obviously not equal to 85 out of 150 or 16 out of 150. Okay, so is there a formula that will sum up why we said 16 out of 64? Well, yes. Okay, so remember that we went away from doing it over 150, which is what you do with the basic, this basic formula that we learned at the start of biology. This would be considering all 150. Given that statement, basically tells us to change that universe figure, that total outcomes figure, to narrow it down. Okay, so that is why we have a formula here that is over P of C. Now we have some notation. This vertical line is given that. So what this means is, what is the probability of B occurring given that event C has definitely occurred? Okay, and this is what we'd call the conditional probability formula. Okay, so what is the probability of B given that C has occurred? Well, it's the probability of the intersection, that was our 16, over the probability of C, okay, or over the probability of the thing we are given. Okay, now this can be quite confusing for many students, and you will want to definitely do a few examples of this. Okay, in the majority of questions, you will see this given that phrase quite clearly. Sometimes it will be a little less obvious and you'll have to interpret that from some other way of saying given that. Okay, but that's one of the harder things you'll do in SL probability.